sharing first. Now I'll go back to sharing. That's a strange event. Okay, so we are recording now, and we are screen sharing. Okay, so try another one, Erica. Just make this calculation. Would you want me to show you how to do it fast? Uh-oh, are you there, Erica? Anybody?
Yes, I'm here. Yes,
okay.
I'm here.
Do you want to try to do this one? I can show you how to do it fast and be confident.
I mean, I mean, that all makes perfect sense. Maybe what I was doing is not converting to z-scores in the right way. I mean, okay, so when you're asking the question, it's less than, less than, less than. Any form of z-score that you're inputting, you know, regardless of the outcome of the z-score that you're really basing it off of, you have to consider that it's the same plus or minus, no?
What do you mean saying plus or minus? I mean, the z-score, the plus side is the same as the negative side. Is that what you mean?
Yeah. So, I mean, I understand that the z-scores only really can tell us about what's to the left.
Oh, yes.
I mean, that's pretty clear at this point. But when we're talking about these calculations, then as they get more and more complicated, the z-score to me gets a little more complicated too. But really, z is always less, and if we're getting z is negative, in this case, right, that we have on the screen, negative 2.25, then it's only going to ever be 0.0122.
Well, no, because I could ask for what's the probability of being greater than 22.
Right. Greater than is 1 minus, and between is, you know, this.
Yeah, right. Okay, so right, as long as you've got that, yes. Right.
Okay, so I guess I'll try it again.
I think you're fighting it because it sounds like you understand it. I am still a little worried about it. Well, I think you'll do well on this too. I mean, just be very slow with it, and but I can show you how to do that fast.
Okay, please show me. Yeah, if you have a quick and dirty method, go.
Well, I think it's a little more sure. So take your calculator, and we'll do this particular one.
Okay.
Okay. Say 22 minus 25.
You have to do the parentheses?
Nope.
Okay. Mm-hmm.
And hit enter.
Gotcha.
Then hit divide for this symbol here.
Gotcha.
Then hit parentheses.
Okay.
Then hit 4. Then hit divide. Then hit second square root, or the square root sign.
I did parentheses on the square root. Should I not?
That's fine. Oh, you mean right there you put a parentheses?
Yeah.
That's okay.
Oh, okay. Maybe I was like, maybe I'm overusing parentheses.
If you did, it would tell you did it wrong, but maybe.
4 divided by square root of 9.
4 divided by square root of 9, and end the parentheses, and hit enter, and you should come up with minus 2.25. No?
No, I didn't. So it's obviously a calculator. It's the way that I'm computing it problem. Obviously, those numbers are very clear, and they have a very direct answer.
Right.
So that's my issue. I'll work it out.
Okay, well, we can work on it later too, but let's get to some other questions too.
Yeah, thank you.
Okay, anybody else?
I have a question about a similar problem. I emailed it to you before class.
All right, I will go try to find it.
Yeah, I was getting the wrong answer, and I'm not sure why. As far as I know, I was doing the right calculations, but...
Well, it's very possible that there's an error in those things. EX. 60.2 and 60.3. You're getting an answer of 0.0466 for this question. Okay, so let me share this screen with everybody, okay, so they can see the problem. New share. So we can all see this problem now. Is it big enough for everybody? The distribution of vitamin C amount in vitamin drops produced by a given factor is approximately normal with a mean of this and a standard deviation of that. If we take a random sample of 16 drops, what is approximately the probability the average vitamin content is between 60.2 and 60.3? Well, what we do for that one is, you know what, I can't, oh, I might be able to write on this. Can I write on this? I can write up here. Reply, I think I can write here, yeah. So we'll write Z is equal to, so we take the upper bound of one of these is 60.3, 60.3 minus the mean, 60, and divide that by, oops, not the question mark, divide that by, standard deviation is 0.5, 0.5 divided by the square root of 16. Well, I saved myself a lot of work, and I was trying to save everybody else a lot of work too by giving you numbers that are perfect squares. So we can just take the square root of 16 as 4. Can I do that? Does that upset anybody? By 4? Or you want me to put the square root of 16 in? I don't know. You won't tell me. Square root of 16. Okay, then we have to calculate that. So I need to get my calculator out. Anybody else wants to try? 0.3 divided by 0.5 divided by 4. I get 2.4. Anybody else get that?
That's what I got as well.
I got it as well.
Yeah.
Yeah.
Good. We're on the same track. Then.
See, I wasn't doing my math the way you're doing your math. It seems like your way is the right way. My way was just getting all mistakes.
Not good.
Not good at all. No, but thank you.
But approximately 2.4 is our z-score.
That's the z-score for 60.3. You now need a z-score for 60.2.
You have to compute them, but okay, so I mean, I think probably some of the other girls in the class, we got those numbers. We kept getting that point.
But you don't have the right answer yet.
Yeah.
Okay. Well, let's see. What's the other number then?
0.9452 is the z-score on 60.2.
So the z-score being 1.6.
Yeah, z-score being 1.6, the probability is 0.9452. And then the probability on 60.3 with the z-score of 2.4 is 0.9918.
0.9918?
Mm-hmm.
And then the other one was
0.9452.
9452.
Mm-hmm.
9452. Then you should subtract those two.
0.046.
And it's not on the end. It's not one of the answers.
No.
I'm sorry, where did you get those numbers from?
The chart, the z-score chart on the end of the.
Oh, the z-score chart. Right. Okay. Okay.
So I was very confounded, and maybe somebody else is too. It's like, where is 0.466 on the answer?
let me do this. Well, I guess I should trust you with this. I presume we're right. Let's see. 2.4, 9918. Sounds good. Way up there, 2.4, 9918, and 1.96, you said?
1.6.
1.6 was the other one? 9452. Okay, well then there's an error in the code, in the problem. There's all I can say at this point. There's an error in the answer. Well, let me see. 9918. 918. 9452. 9452. 466, right? Yep. I just have to. Okay, so I guess there's an error. This is a correct number. Which quiz was this on?
13.
Quiz 13.
But the funny thing, that's why I was using these same equations, and on quiz 13, for some reason, I triple checked and I wasn't getting. I had similar problems with other questions, and I don't know if anybody else did too. And I'm not, I don't know. All I know is that I'm using the right formula for the right question and plugging them in and coming up with this kind of issue where the answer wasn't part of the multiple choice. Has anyone else encountered that on quiz 13?
I have, yeah.
Right, that it's like the 4 answers. Well, you triple checked it, and
I got
Definitely.
I got one wrong that I knew was right, and I emailed your helper. I'm not sure who it is that does the grading, and they agreed with me and said that it would be fixed, but it hasn't yet been fixed. But so I'm hoping.
Well, I didn't know about this until this instant. Well, all I can I can make up excuses. I don't know what they would be. I mean, there's a lot of transferring of things and copying that goes back and forth, and that is very difficult, to tell you the truth. But I will go through chapter 13, and if you tell me what the errors are, I can fix them for you. I mean, I can fix your grades for you, but I can't do much beyond that because I don't know specifically what the issues were. But I'll go through 13 and fix everything, but it is probably a little late, except for next time. I don't know what's happening with these quizzes. I mean, it's just been a disaster this whole semester, with dates and this kind of stuff. I haven't had this problem before. But anyway, that's my problem. We'll solve yours. Is quiz 13 closed?
No, you have it open as well as 14 until tonight.
Okay, well, I can't change it while it's open. I can't modify, add, or subtract problems. Mm-hmm. So I'll have to change it afterwards. But if you tell me which problems that if you tell me which problems you think you have right, that you got wrong, we can correct the scores. How's that? By the end of the night. Tomorrow morning, just email me something and I'll take care of it.
I mean, I know the quiz has already been extended because of issues with the video uploading. I mean, is there any way to, extend the quiz again and give us time to, for those of us who have worked all day and been very confused why the answers are not coming out correctly, even though we've done our best with the formulas? Is there any way to say, okay, let's give everyone a chance to assess it?
Well, if I
Yeah, why not just close it and then fix it and extend the time to take the quiz until at least the end of the week?
Yeah, that's just what I was thinking, is I could close the quiz now, fix it, and then open it tomorrow.
Okay.
But how's that going to affect people who have 15 out of 15 on it? Is that going to make it so that they got those ones wrong? Since you're going to...
You got 15 out of 15. No, I don't think it...
If you change an answer and then resubmit the quiz, isn't that going to change the answer that people got just for taking the quiz a couple of times?
Right, because like I got this question, but I was getting the wrong answer. But there was another student who was saying in the chat that they just chose the option that was closest to the answer that we were calculating, and then it marked it correct. So then now if you change it,
I don't know if that's going to change or not.
Would it be easier if people just emailed you what they think is the right answer so that you can correct it? And they
That's
can
what I was suggesting.
Yeah, because that way you don't have to change a whole quiz, because with the quiz is still open, I haven't finished doing quiz 14 yet, and I don't want you to go in and change it if I'm in the middle of taking a quiz. So if we can just email you what we think the right answer is, and then you can get back to us and change it instead of having to go back through and try and change everything. It's just, I think, would be easier.
Right. Yes, that is easier, but you need to email me. You need to tell me what the problem was too. Tell me, give me your name. I see everybody has a different quiz, and if you give me it was number 7, that doesn't mean anything to me, because they are in random order. So if you let me know. Let me know, take a screenshot of the problem, tell me your answer. That'll work. How's that?
works for me.
Yeah, that works good. I guess I'm just still confused how, if the right answer wasn't one of the 4 choices, then how in the world did approximating it get you the right choice? Maybe that's just a function of...
Oh, they got lucky, yeah.
Just guessed and it got marked right.
Right. Like that problem with the 16 on it. It's likely it's possible that 16 could have been a 25, which would change the whole answer, and maybe it's the correct answer. Maybe that's the closest one.
Right.
And that's what usually is the case, because there's just something minor in the differences.
Okay.
I mean, there's something minor in the statement of the problem generally. And that's just one of the numbers that's off a tiny bit, which changes the answer, which changes the whole thing. So just send me the issues. This is one of them. But let's see. So you have to send me the issues. Right. That's all I can do at this point. And I'll go through tomorrow after this quiz closes and fix them. Fix the problems.
Professor, could I ask a question about chapter 14?
Yeah, of course.
Is it okay if I post the question in the chat window? Are you able to get it that way?
I believe so. Let's see. I don't know what this more means. Okay. Yeah, I have to stop sharing my screen to get it. For some reason. Pause share. Stop share. Okay, you're going to put it in the chat window?
Yeah, I just did. It starts with after a week-long fishing trip.
Oh. Did you really go fishing?
No.
Okay, here's the quiz. Oh, is this Nicole?
Yes.
Oh, this is the problem. Okay, you went
After a week-long fishing trip in
100 rainbow trout. Oh, this answer is not trustworthy.
Oh, why is that?
Because you threw some of your fish back.
Seriously?
Because you went fishing and you tried to find the average length of all the fish, and you took a sample and you didn't like some of the sample and you threw it away. So it's not a trustworthy sample. It's not an SRS. You put a bias in it by throwing away fish.
Okay. That would be why I got it wrong.
Yay, I got one right.
Could you go through it as if you had not had the you put some back aspect? If it was just 100 rainbow trout and stuff?
Sure. I'm not sure that any of those numbers will be part of that, but because I just kind of made them up, I expect 22.
Well, I got one of them as the correct answer, so
Okay.
that's why I was confused.
Standard deviation. So the confidence interval would be, so the error, M, margin of error, is 95% is 1.96.
Uh-huh.
1.96 times 4 divided by the square root of 100, right? 100 fish?
Yep, that's correct.
Okay, so that's 1.96 times 2 over 10.
Yep.
And that turns out to be, I bet you have the answer. What is the answer?
4 over 10, right? 4 divided by the square root of...
4 over 10, yeah.
Yeah, okay. So I got 0.784.
0.78. Okay, so then the answer would be A.
If it weren't for the you put some back.
Yes.
Okay.
So you got it right.
Okay, good. And then in regards to the chapter 17 stuff, did you get a chance to fix that and narrow it down to what we were actually responsible for?
It is 99% fixed. I can tell you what you're responsible for. All that is not available there's two things that aren't fixed yet. Let me pull up the schedule, okay?
Okay.
To talk to. Get rid of this for now. Let's see here. Well, I'm going to pull up the schedule. I need to do this. Course, that's what I want. That's the course. And then I will screen share this. Share screen, which will be this one. Okay, we can all see the schedule now.
Yeah.
Okay, so what you see from my side is chapter 17, the PowerPoints.
Uh-huh.
Okay. Now the chapter 17 PowerPoints are going to include a confidence interval. You see this black part here?
Mm-hmm.
You won't see that on your screen.
Okay.
I've hidden it. And I have hidden this video for now, anyway. And I have replaced it. Oh, I've got, where is that? Where are those videos? Where are those videos? One main hypothesis testing. Why did I say 1B? When was this posted? Let me check something here, okay? Not that one.
On the last screen, would it be maybe under the video tab that you usually post videos under?
No, this is the video that I want.
Oh, okay.
195B. I can double check that one real fast. 195B. I'm pretty sure that's what I want. Chapter 17. No, that's not it. 530, 351D. Okay, that's an older one. 351D. Ah. I'm working at it, gang. The videos where, let's see, additional resources. Can't figure out what happened to those videos I posted. I added.
Which videos are you talking about?
I have added for chapter 17. Oh, let me get this straight. Oh, I think, okay, here's what, yeah, these are the 4 videos for chapter 13 that I added. And there's a chapter 14 part 1 video, and I think that was already there.
Yeah, that one was already there. And then I haven't even had a chance yet to look at chapter 14 or 17 personally. But I also didn't necessarily want to because I wasn't sure if it was accurate, and I don't want to start learning material that we're not going to be responsible for and confusing myself. So is the material for at least chapter 14 accurate?
Yes.
For the second part of chapter 14?
Yes.
Okay. And then it seems like you may still be working on the chapter 17 material.
Well, I still am working on it, but it should have been much more clear than this. I'm trying to, oh, I think this is the new video. Yeah, that's the new video. Let me see this one. That's the one I had hidden. I hid the wrong one. 195B. Introduction to T-tables and hypothesis testing with one sample. Well, okay, I can add this instantaneously because I have the video link here. Let's not worry about that for just a second. I'll tell you what we're going to do. Okay.
Okay, I just want to know what I'm responsible for.
Exactly.
So I can at least read that section of the book. And then I can catch up with the videos before I do the quizzes afterwards, after you put them up. Okay. I just want to make sure I know what I'm going to be responsible for in regards to what is actually going to be on the chapter 17 quiz and the exam.
So here's what we're going to, here's what I would like to have done is all of chapter 14. That's not changing any.
Okay.
So chapter 14 isn't changing.
Everything about module 7 is going to remain the same, good to go.
Yes.
Okay.
Chapter 17 has 3 parts to it. It has the t-distribution, which we have to figure out how to do, and that's the one I'm pretty sure I made. Okay, and that's the one I've got. I've got it. I thought I had uploaded it, but I don't see it. So we need to see a video for chapter 17 on how to use the t-distribution.
Okay.
Okay, then you need to learn how to use the t-distribution to solve a one mean hypothesis test. And then we'll have to learn to use the t-distribution to solve a two mean hypothesis test. And I thought we did, actually I think I've made 2 of those three videos, but they're not up here. So I'll have to find them and upload them. So here, you know what? I will send out an email saying what you have to do in 17. Okay, the top.
Okay, and then I'm just worried that because the things are being changed around, that the quiz is not going to be reflective of what things have been removed, and then therefore I was surprised by having chapter 7 in the second exam, and so I just don't want to be surprised in exam 3 with things that I don't actually know
and aren't required to know.
Yeah.
Well, that has been what has been taking up the majority of my time, is changing the quiz questions around.
Okay. Okay.
It is unbearably tedious because you can't see the whole question. You can only guess at what it is, and you have to change, and then you have to pull it out. And if it's not right, you got to put it back in, and it's just really, really tedious. But I think I've got a set of questions for the quiz 17 that we need. So we'll have a set of quiz questions for 17, and then I still do have to learn how to pull only questions from my new quiz 17.
So basically we should not plan on taking the exam 3 until you have sent an email saying that for sure it's all ready to go.
I would do that if I were you, yes. And that's going to, and I'm trying to get that done. I hope to get all that done tomorrow, but end of the year, well, I'll try to get it done tomorrow. Okay?
Okay, thank you. Yeah, because I'm planning on working on that stuff this weekend so that I can get it done and not have it for next week.
Okay. Sounds fair to me.
Okay, thank you so much.
You're welcome. Anybody else?
I'd love to go over the second part of chapter 14.
The hypothesis testing?
Yes.
With slides kind of thing, or how?
Yes, that'd be great.
Okay. Introduction to hypothesis testing right there. All right, let me get rid of some of these other things that I have going on here in my screen. Screen seems to be inundated with stuff. Okay, introduction to hypothesis testing. PowerPoint slides. Introduction to that. Let me share my screen again. Reshare. Stop share. Share screen. Share. Okay, so we're doing hypothesis testing. There's our goal, but let's just march ahead and see what happens there for a while. What we have to, see, let me, okay, so let's look at this problem. So what you have to do is you have to set a a null hypothesis, which is called H naught, H0, and HA, which is the alternative. And then you have to set a level of significance. And this is called alpha, Greek letter, alpha, and this is on the order of 0.05, 0.01, 0.025, but it's a small number. And it represents more or less the probability of making an error of a certain type. The HO and HA are hypothesis. The HO is generally the hypothesis of the status quo, which means, well, we'll get to an example, but that'll show you better what it means. But HA is somebody's thought that here's an alternative to what the current status is. And so this is kind of what we're testing to see if we think it's true or think it's false. But we have this hypothesis, H naught, and we have this alternative that somebody's trying to prove. We have to, and then we have this level of error called alpha, and we have to set a decision rule. And that decision rule is, and you don't know what these numbers mean yet, but if the p-value is less than alpha, then I will reject H naught. We'll talk about that. But how do you get the p-value? Well, you have to compute a z-score, then you compute the p-value from the normal table, then you make a decision, and then we state a conclusion. So that's kind of the process. So here's an example. You are in charge of quality control and sample randomly 4 packs of cherry tomatoes, each labeled as ½ pound. The average weight, well, 227 grams. The average weight, though, is only 222 grams of the 4 packs. So the problem that you would have as a quality control person is, am I packing my boxes of tomatoes that are supposed to be ½ pound, but are less than ½ pound? Am I cheating the customer? I need to know that. You could be packing it with 232 grams. That way you would be cheating yourself, the company. So you need to know it either way. So, but now you can have, I mean, you picked 4 packs of cherry tomatoes out of a bazillion, and it's going to vary a lot. Is this due to chance? Just a chance of those 4 being bad? Or is it really bad? Is there enough evidence to say it's really bad? Well, the enough evidence comes here with this alpha. The smaller I choose alpha, the less likely I will be to make that kind of an error. But there's another type of error that we have to worry about too. But that's kind of the process. Now we just have to go in and see how to do these things. There's the null hypothesis. So the null hypothesis in this cherry tomato case is that, hey, we are doing a ½ pound. We are right. The alternative is, no, I think we're packing it less than what the ½ pound is. We don't know, but we think it might be. Okay, so that's the H naught and HA. Well, there we're showing. Well, so here's how we do that with hypothesis testing. So we would let mu be the average weight of the whole batch of tomatoes, packs of tomatoes, the whole, all of them. And we're claiming that's 227 pounds. That's what we think it is. But is it really 227? This is the alternative. Mu is not 227. So that means that maybe it's smaller, maybe it's larger. I don't know. But let's find out if we think it's not 227. I'll show you some other examples. We changed from 227 to 12, but just numbers, okay? So here we're thinking that the null is 12. I don't think it matters where the 12 comes from. But there's 3 alternatives, and only 3. it might be that that we think the population is less than 12, which would be, this is HA, mu is less than 12, is HA mu is greater than 12, and HA mu is not 12. So those are the only three possibilities. Now note a couple of things here. 12 is here, 12 is always here. These are the same numbers. That equal sign is always on H naught, and HA always never has an equal sign. It can have a less than sign, it can have a greater than sign, or it can have a not equal to sign. This arrow points to the left, so this is a left-tailed test. It's also called a lower-tailed test because it points to the left, or where the lower part of the curve is. This is a right-tailed test because the arrow points to the right. It uses the upper tail portion. This is a two-tailed test because it has to do with plus or minus. It can be greater than or less than. So this is a two-tailed test. We have to treat these all slightly differently. Just slightly differently, though. Okay, and our level of significance is, like I was saying, is a small number, 0, 0.1, 0.05, 0.01, etc. So in theory, alpha can be any number between 0 and 1, but nothing else. It can't be outside of 1 or 0. It can't be greater than 1 or less than 0. So here's a specific problem that we can look at to see how to solve. This is an old problem, as you probably know when you see the numbers. The average amount of healthcare, the average amount spent on healthcare by U.S. citizens over the age of 18 is speculated to be $12.50 per year. Well, that might have been true 20 years ago, but probably not even then, with a standard deviation of $138. Okay, so what we have right there is this is given conditions. The mean is 1250 and the standard deviation is 138. A special interest group thinks that this amount is inaccurate and hires an independent third party to investigate the claim. So they sample 17 citizens and they produce an average health care of $13.88. Well, my 1388 is definitely bigger than 1250. So, but that doesn't mean that the average is really bigger than 1250. All it means is that these 17 are bigger than the average for these 17 people is bigger than 1250 and quite a bit larger. But is it large enough to cause a difference? Is it large enough to statistically say there's a difference? It's not 1250, it's greater than that. So the first thing we have to do is state H naught, HA. So H naught, oh, this is supposed to be a quiz. Can you see this here down? Let's see, did I do that? Excuse me. So this was a practice problem. Can you see this? Let's do this, I can do that for you. Can you see that print down there at the bottom? Somebody answer, please.
Yes.
Okay.
Yes. Yeah.
Okay, so H naught, mu is 1250. HA it's not 1250. We don't know if it's bigger than or less than. N is 17, standard deviation is 138. X bar is 1388. That's all data that's given and we can translate that. Okay? So the next, okay, this is another similar problem, but let's go back. Let's see, is this the right problem? No. I jumped around here quite a bit. Just hold on a second. Okay. Let's go back to this slide and I can talk about that for just a second. This is a slide that we were just talking about. Here, this slide is there simply to set up the problem. Okay, so we've got the problem set up. We now have to test to see whether we think that's right. Now I've got some, and here's another problem just to set up. You can work through, you can read through this to see if the setup is, if you understand the setup for it. And let's not take time to do that. And I can't read this one because there's a bar in the way here. There's an active ingredient. Okay, so that's just another. I have found that the students have a hard time setting up H naught and HA. And so I put in these slides to give you a lot of examples. So in this case, is the active ingredient concentration as stated on the label. What it states on the label is 325 milligrams per tablespoon. Well, it's frequently easier to set up the alternative first. And so sometimes you want to say, well, is it the same as 325? Well, I would say HA is mu is not 325. And then H naught would have to be mu is 325 because the H naught has to have an equal sign, and these two numbers are the same. Okay, let's not do any of that for now. Let's get to how do we solve this? This is, all right, yeah, here's the other half of this portion of the problem. Here's a separate hypothesis. Mu is 12, HA mu is less than 12. Now we have to make a decision about what we believe. And in hypothesis testing, there's only two possible decisions. And that is I reject H naught or I do not reject H naught. I fail to reject H naught. Those are the only two possible decisions you can make. You don't make any decision about HA. You just make a decision about H naught. So we can decide to reject H naught or to not reject it. We'll talk about how to do that in a bit. There is a specific rule, and that rule is reject H naught if the p-value is less than alpha, and do not reject if the p-value is greater than alpha. So we just have to find the p-value, which I'll show you how to do that in a slide or two here. Two important points. You cannot make a decision about HA. You don't make a decision about that. You cannot, and the other point is you cannot prove H naught is true and you cannot prove H naught is false. My data will only suggest that it's true or suggest that it's false. A quick example is that if you think of yourself in a court of law, you are the defendant, say, H naught is you are not guilty. Mu is you're not guilty. HA is that you are guilty. And that we have to have that my decisions are that the decisions really should be, I either reject this, thinking that there's lots of evidence to support this side, HA, or there's not enough evidence to prove I'm guilty. But I can't prove it either way. I just come to a conclusion. Okay. And we have to, and so here, how do we calculate the statistics for it? You start by computing the z-score again. Everything revolves around the z-score. So that's the same formula we've seen over and over now. Okay, so now how do we compute the p-value? Well, suppose we start with a left tail test. And as I said earlier, the computing of the p-value is slightly different if it's a left tail test or a right tail test or a two-sided test. I'll go through each example. So if it's a left tail test, like this one, and my z is given that z is minus 1.84, then what I do is I go to the normal table and I find the left area associated with z equal minus 1.84. And I get that area to be 0.0329. So if you have your table in front of you, take a quick glance and you'll see that 1.84 has area to the left of 0.329. So what that means, and it's simple in this case, is that the p-value is whatever that area is to the left, 0.0329. And if you go back to this slide, a couple of slides earlier, step 2, reject H naught if the p-value is less than alpha, is the rule. That's the rule.
I'm sorry, Professor, is it the Z table or the confidence level C table that we're getting that negative 184?
Well, you need it for the Z table. What's the C table?
Never mind. No, the other one we were doing with the 90% and 95%.
Oh, no, you need the Z table.
Okay.
I guess that's, I have it marked as table C.
No, that's fine. Okay.
No, it's not. It's table B.
All right.
That's
Thank
table
you.
B. The T is, it's table B.
Okay.
Right, that's the problem. It's table B.
Professor, how did you get that number?
1.84?
Yeah.
I'm making it up.
Oh,
Okay, so I made it up, but you would get it from this slide.
Can you do that equation? Because I kind of get it wrong when I'm trying to get my numbers through that.
Yes, I will do that equation in just a moment.
Okay.
Okay, because I have to get some numbers, and we'll get some real values in there with a real problem. I don't have the sufficient data shown here at the moment. I just have that a z-score of -1.84 came out of some data. So what I'm showing you here are all the steps necessary to do a hypothesis testing. You want me to do and you want me to find a problem and go all the way through it
yes, please.
right now?
That'd be very helpful. Thank you.
Okay, let's just do this one then. We'll go this one from a long time ago. Okay. I don't have the z value here. I can make the z value for us. The z. Okay, so this is the health problem. We have we have that mu was 1250. Mu is 1250. Let me. So for our problem, I'm going to have mu is 1250. X bar is 1388. Population standard deviation is $138. Where's my sigma? No, I don't have one. Standard deviation equals $138. Okay, and n is how many? 17. Equals 17. All right. So see what happens to my m, the mu. Okay. So my z-score is going to be equal to 1388 minus 1250 slash, that's standard deviation, isn't it? There's no y's in standard. 138 divided by the square root of 17. And that should give us the round number of 12. See, so here's how I do this. I will just say as I walk through this, I will take a 1388 minus 1250 and hit enter. That gives me the numerator. Then I will divide that by parentheses 138 divided by the square root. I have to do my square root of 17. Oops. That doesn't like that one. 17. I think that's not going to like that. Yeah. I don't like this calculator. Hold on a second. You know, I have this done over here. Let's just get to it fast. Oh, needed stats calculations. We need 1250 for the mean, 1388 for this part. The sigma was 138 and the mean is 17. And my answer is 4.12. So I'm getting 4.12 here. Anybody else get that? Nobody else got that number? Hello? Anybody there?
I didn't do the math, so I'm just paying attention to what you're doing.
Okay. So I get a z-score of 4.12. Well, man, this is bad slide too. It's a bad example. Well, it's not the first one that we should see, and it probably isn't. But if you go to your z table, you'll find that there is no 4.12 for z. This is table B, and you'll find there's no 4.12. So what that means is that, see, you made me go to to give you a quick example, and we haven't been through the rest of this stuff yet. Well, you're just going to have to deal with this example for right now. I'll find another example. We can do a different one. But here's what happens. The z-score is 4.112.
Professor, I'm sorry. I just did the math and I didn't get that answer.
What did you get? 138?
I got 0.2425, so 0.243. I don't know if I did something wrong.
Yeah, I actually think I'm probably closer to being right than you are. I think this one's correct, unfortunately.
Well, because 1388 minus 1250 is 138. So when you divide that by 138 divided by square root of 17 in my calculator, that's what I get.
Right, but so you're probably not putting your parentheses in the correct place.
Oh yeah, I didn't. Hold on. 138 divided by square root of 17. Okay, yeah. Sorry, I didn't do the parentheses.
Yeah, I got 4.123.
Yeah.
Okay. Well, so the problem with this is that the z-score is not in the table, and so what that means is that the z-score is way off the top of the table. All right, now you're going to have to fight through this one. Okay. So look at your the z-score of 3.4. So if z is 3.4, the area to the left is 9997, almost 1. .9997 when the z-score is 1.8 or 3.4. When z equals 3.4, the area to the left is 997, which means that the area to the left of 412 is really, really close to 1, right? because 4.12 is bigger than Z, and it's the area to the left, you need to draw a picture maybe to see what happens. And so now this is so the area to the so what you really want from the hypothesis testing is you want the tail area. You want either tail area, the right or the left. So so the Z is 4.12. The tail area to the right is almost 0. Correct?
Yes.
Okay, good. Thank you. Thanks. So the tail area to the right is almost 0. This is a two-tailed test. And the rule is for a two-tailed test, you have to double the p-value that you got on the right. And so 2 times 0 is still almost 0. This is a bad example to start with. I didn't recognize this when I started this particular example. I'm sure there's others previous to this that are better.
Yeah, but then why would you put a bad example in the slides that we're trying to study off of so we can try to figure this material out?
Because there's previous slides that tell you how to do it easier.
Okay.
This brings up this one brings up a separate point.
Okay.
Is what happened here.
Okay.
This is a separate point that, for example, here's a test. This particular one has a Z of, so this is a two-tailed test, and instead of getting 4.12, I got 2.116. And now we go look this up in the table, and you get 9846. But we want the tail area, so we take 1 minus that. That gives me the tail area of 0154. But since this is a two-tailed test, I have to multiply by 2. So the real p-value then is 0308. The p-value is 2 times that, two times the tail area.
Is there a slide where you have like the rules for the p-value showing if it's a two-tailed, you times it by 2, and if it's a one side, you do something else, or the other side? Like,
yes, I have a much more comprehensive set of slides for you in a video that is done, and it's a much better set than this stuff.
Okay.
For the two-tailed test. And that's the one that I thought was loaded that is not loaded. I don't want to sit here and listen to myself talk. Oh, I could get those slides out. Do you want to spend another 20 minutes?
Sure.
Anybody? Who else is there? How many are here?
I'm here.
I'm here.
There's 14 of us still here.
There's 14. That's well worth it. Let me pull up this other set of slides.
So then the video that you thought was posted and is for chapter 14 or for chapter 17?
17.
Okay.
Can I ask a quick question about the discussion board assignment?
Sure.
On the assignment, it says that we need to use the Excel to fill in the chart on the Word document.
Uh-huh.
So we don't need to figure out anything else. We just plug in the numbers and fill it in.
Yep, it's pretty easy.
Okay. Because someone else had posted on there that they had emailed and asked, and that you had said that you had to actually find the probability of the true positive and then divide it by all the positives. But that would be different than what we're calculating with the Excel.
I don't think so. I mean, I don't remember the specific questions that I asked, but that would be a specific, that would be a typical question to ask.
Because the whole chart was basically filling out the true positive, and I believe it was the false negative.
Okay. The true positive would be all of those with a See,
positive test with the disease.
divided by all of those with the disease. See, that question is find the probability of having cancer given that you have a true, or given that you have a positive.
Okay.
So you have to find all the positives and then and then divide that into all those that have cancer and are positive.
Okay, because the way that it was set up and the way that the instructions look is that you just plug in the numbers that are given on the table. So the numbers that are given are the prevalence, the sensitivity, and the specificity. And then it does it for you, but it doesn't. I didn't realize that at first, so I kind of had done it both ways, and then I wasn't really sure which one you were wanting. So is there any way you could just go over one of the examples? That way we know which way is the right way to do it.
Yeah, let me go finish, but let's finish this one thing first.
Okay.
Okay. Okay, so actually, okay, I got to backpedal here again. The slides I put together today were for chapter 17. And chapter 17 uses hypothesis testing for, I mean, it does the same thing for hypothesis testing, but with a T distribution instead of the Z. Let me just look at this for a second, okay? See if it would maybe make a little more sense. Let me go back here for just one more second, okay?
Professor, sorry to interrupt. I'm going to have to go, but I'm still interested in seeing what it is that you're doing with this part as well as the discussion board topic. So can you please keep recording for all of those portions?
Sure.
Thank you so much. Have a good night.
Thank you. You have a nice night too. All right, let's look at these slides. Let me share the screen. Stop share. Share screen. That would be this screen. Okay, and pull this up. They're going to look a little different, but forget all this stuff up there, but it's the same kind of thing. Students going to learn about hypothesis testing, null hypothesis, H0, alternative, decision options, type 1, type 2 error, and significance levels. So we did this. Hypothesis test consists of two hypotheses, the null hypothesis. And in this case, I'm doing H0 and U is 22. And the alternative hypothesis is when we think there's something else that's true other than what is what we believe is true. Now we have been assuming mu is 22. We now think that it's different than 22. In this case, I'm assuming mu is greater than 22. I'm thinking, is it greater than 22? I'm asking that question. And the other alternative is mu is less than 22. And the third alternative, of course, is mu is not 22. And then we need a significance level, alpha. And so the significance level is to tell you what type of error you might make, how big your error might be. And we have, for example, alpha is 0.05, and just what I said, alpha is allowing for a decision, for an error. And we make a conclusion. Our conclusion is, say, our decision is about H naught. And if we decide to reject the null hypothesis, that's okay, but our conclusion is about the alternative. We will conclude data provides sufficient evidence to support the alternative. We reject this and support this. So data supports HA. If we did not reject the null hypothesis, then I still make a conclusion about this. I don't say that H naught is true. I make a conclusion about this. I say that there's not enough evidence to support HA, mu is 22. So those are the conclusions that you can make. When you make a decision, okay, we have our H naught, and H naught could be true, and it could be false. We don't know which is the case, but it could be either one of those. We will make a decision. We will either reject H naught or not reject H naught. If I reject H naught, but it's true, I've made an error. That one's called a type 1 error. If I do not reject H naught, and it's false, meaning I should have rejected it, that's called a type 2 error. And these two other options are correct decisions. If I do not reject and H naught is true, then I've done the right thing. If I reject H naught, but H naught is false, I've still done the right thing. The other two are errors. Okay, so there's the word saying just what I said. The interesting thing here is that the probability of a type 1 error, that's this error right here, is alpha. So when you specify alpha, you're specifying this value here, the probability of making a type 1 error. And remember, the type 1 error was rejecting the null when the null is true. And the type 2 error is called beta, but beta is very hard to calculate. We set alpha. We set alpha. Beta is a hard thing to calculate, but 1 minus beta is called the power of the hypothesis test, but that's okay. One thing you do need to know is that you can't get low alpha and low beta. They go in opposite directions. If you can make alpha low, beta gets bigger. If you make alpha high, beta gets smaller. So you got a trade-off. You can't get both. Okay, that was the end of that set. So the critical value approach to this hypothesis testing. The process is we're going to read the problem. We're going to state the null hypothesis, obtain the significance level given in the problem, compute the z-scores, forget t-scores for right now, make a decision about H naught, and either reject H naught or do not reject H naught. Then we're going to make a conclusion about the alternative. So our problem is, how do I compute the z-score, and then how do I make a decision? Well, how do I make the decision is what we're going to talk about. The decision comes from the significance level. It's based on the significance level. There's two approaches to making a decision. One is called the critical value approach, and the other one is called the p-value approach. And the book does both cases, and we'll look at how to do both. Both approaches require knowing the test type, remembering that it's left tail, right tail, or two-tailed. And left tail test was this one. Right tail test is that one. Two-tail test is that one. So we need to know which type it is for either of these approaches. And here's how you'd use the critical value method. We obtain that from the level of significance, the test type. Divide the normal curve into two regions, the rejection region and the do not reject region. And I'll show you how to do that. For a left tail test, I'm going to have, here's my normal curve. For the left tail test, my rejection region is this tail area here. And the do not reject region is this area. What that means is that if once I compute my z-score, I can tell, okay, for the critical value approach, I will look on this line and say, well, where's my z-score? If my z-score is in here, then I will reject H0. If my z-score is out here, I will not reject. And that's as simple as that. You just have to know how to divide it. Well, I'll show you how to divide it in just a second, but look at the other rejection areas. So for a right tail test, the z-score has to be up in the top right corner, the right tail area. That's where the reject for the right tail is. For the left tail, it's over here. No, right, scrap that. The do not reject region is all the way to the left here. The reject region is the right tail. For the two-tail test, you can fail on either the left side or the right side. We still need to know how to draw these dashed lines. And that's going to be shown on the next slide. In any case, and this is important, in any case, the total area, either the left tail or the right tail or the two-tail, which means I have to add both of these together, the total rejection area is equal to the level of significance. So if alpha is 0.05, this region has to be 0.05, this region is 0.05, and each one of these is 0.025. Okay, so the critical value approach, level of significance is 0.05. So to get the critical value, we start with a hypothesis test as left tail. And so to find the critical value, what I do is I look in my table and I look up 0.05 in the body of the table. And if you go look in that table B, you'll find that minus 1.645 is right here, and that tail area is 0.05. So my critical value is 1.645 for a left tail test. So my rejection region is to the left of 1.645, and do not reject is to the right of 1.645. That means when I get my z-score, if my z-score is bigger than 1.645, if it's over here, I do not reject. If it's in here, I do reject. Total rejection area is alpha again. And here is a summary of the rejection regions. So here's the level of significance you might choose, 0.1, 0.05. These are the typical ones. And here's Z alpha over 2. That's okay. The total rejection area, okay, now if I have a 0.1, so go look up in your table at minus 1.28. Minus 1.28. Minus 1.28, and you will get 1003. So the area to the left of 1.28 is 0.1. The area to the right is of 1.28 is also 0.1. But alpha over 2, which is what I need for the two-sided, is 1.645. Because now I need, my alpha is 0.1, so I need alpha is half of 0.1. And so it's 0.5. So I need to then find in the body of the table where 0.05 is. Maybe if you study this chart a while, you can figure out what these areas, where these numbers are all coming from. Regardless, you have them in front of you now. Okay? You have them in front of you. You can, I will post this for you. Okay? I don't know if we're going to want the whole thing or not, but we'll get most of that. So that's the end of that section. You interested in going on still? Anybody?
Yeah, you can go on. There's like 9 of us in here.
You still have 9. Okay. Questions? Nobody?
No. It's the level of significance is still kind of confusing to me, but it's going to be given in the questions typically.
Yes.
Is that right? Okay.
Yes. Yeah, it's just the probability of making an error of a certain type.
Uh-huh.
And so you want to choose that you get to, I mean, you don't get to choose it for the problem, but the manager will get to choose what the error level is. What type, how big of an error can I stand? So if this is a project worth $100 million, well, I want my alpha to be small. But if it's a project worth $100, I might not, my alpha could be larger and I wouldn't care much. If it's a medical thing, you want your alpha small. There's a big trade-off, and it's a study in itself as to how to do that. But right now, it's just an alpha that's given to you.
Okay. And why do you divide it by 2?
Because, oh, you mean for this column?
Yeah.
Well, yeah, that's unfortunately, that looks like it's a little confusing. You need the Z alpha over 2 for the two-sided test.
Oh, okay.
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 Actually, I think that's probably wrong. I think that should be Z alpha. I think that would make it. I don't think that column should be there, period. I think we should just ignore this column. Okay. And this is what you need to look at And I should probably put over here alpha over 2. That would probably make this more clear.
Okay.
Yeah.
So anytime the problem has a level of significance of like 0.1, and if it's a left tail, we're going to use that Z-score.
Yes.
Okay.
If it's left tail and it's 0.1, you use that. You use this as the critical value.
Okay.
This is the critical value for a left tail test. This is the critical value when it's 0.05. The critical values here for two tail, if it's less than minus 1.645 or greater than plus 1.645. Remember this chart here somewhere. The two tail, I can have an error here, which would be greater than 1.645 or less than minus 1.645.
And you add those together.
And if you add those two areas together, they equal alpha.
Okay. Okay. So why did you times by 2 in that other problem for a two-tail problem?
Because the p-value, you'll see why.
Oh, okay.
Okay?
Okay.
That's the p-value portion of it. Okay, so here's the p-value approach. I like this better, tell you the truth. So we start with a hypothesis test, 234 this time. And it can be left, right, or two-tail. That's the first major difference. We don't care what type it is just yet. Perform the experiment, and I'll get a Z0. I wonder what that is, a Z-score. With results of experiment. So I perform an experiment, and I calculate the Z-score. I don't know what this is doing here. The p-value is the area shown in the plots below. So, oh, I see what I did. So I get a z-score equal to z sub 0. That's what that's supposed to be. Z sub 0. I'll make it better. So I'm calling my z-score z sub 0. So I get my p-value is in these charts. So I look at my p-value, or my z's not, and I put it on the axis. If my z naught is on the left, I should have a left tail test, and then my p-value is this area, simply this area. And I get that from table B. If it's a right tail test, my p-value will be over here. And the p-value then is the area, the tail area of the right side, the right tail area. And Z naught is here still. This is the rejection region, the blue. The blue is the rejection region, and the non-rejection region are the white areas. Now, here's why I multiplied by 2. When I get a two-tail test, I get a Z naught. Well, the Z naught can be positive or negative. If it's positive, it's over here. If it's negative, it's over here. But either way, I can get a tail area. So if it's negative, I get a tail area on the left. If it's positive, I get a tail area on the right. But the p-value is the total tail area. So if I get an area on the right, I have to multiply it by 2 to get the total p-value on a two-tail test. That makes sense? Do you see now why we multiplied by 2?
Yes.
Because in the previous example, I got a Z naught, I think it was positive. So I just got a positive number here, and I multiplied by 2 to get the total p value. Okay, and the area equals the probability of making those kinds of errors. And the rejection rule for the p-value is very, very easy. Reject H naught if the p-value is less than alpha. It's that easy. So this is why I like the p-value better. I don't have to deal with all those critical values. The p-value is a much cleaner approach. The hard part about the p-value is that you have to multiply by 2 here for this case. Okay, so that's the p-value. Well, let's not deal with this just right now. You can look at that later. We don't need this either for right now. Oh, that would have been good. So here's some worked out hypothesis test problems when the standard deviation is known. Eating out. This is the left tail critical value approach. And we have 700. See, it's the problems I get are interestingly accurate. They all give most of them give a source for all the data. So this one was interesting to me. The number of meals prepared at home is less than 700 meals per year. That's kind of amazing to me. So they didn't give me the standard deviation, so I made one up. Now I want to test this and see if it's less than that. So I want to So I think maybe the number of meals prepared at home is less than 700. And I take a sample, 64, get 680 meals prepared at home as the average. Test whether the population mean number of such meals is less than 700 at a significance level of 0.025. So there's the hypothesis. There's the level of significance. There's N, and there's the standard deviation. Just write them all down, and you got it. There's X bar that comes with the data too. Now I compute Z-score. Just plug all the numbers into that equation we've seen, and I get minus 1.82. And remember, we're using the critical value approach. So I have to go back to my critical value and find out for a 0.025 left tail. Oh dear, I have a 0.05 here. Well, this is for 0.05, sorry. The critical value is minus 1.96. But regardless, so let's go with this one. And what I would get is I would not reject H naught since my Z-score is greater than the critical value. Minus 1.82 is greater than minus 1.96. So I do not reject. For left tail test, it has to be less than. Remember back here at this slide here? Way back here, sorry. For the left tail, it has to be in the left area. The p-value has to be down here. And my critical value is bigger than that. Okay, so, and then I state my conclusion. There is not, evidence cannot support that fewer than 700 meals are prepared at home. See, my HA was, mu was less than 700. Okay, the right tail approach to this is a different problem. And I'll let you read that if you wish, but it boils down to my H naught is 1250, mu is 1250, my HA is mu is greater than 1250. The rest of the data is given to me like this. Alpha is 0.05, N is 20, standard deviation is 147. Should all be given in the problem. Next bar is 1310. I compute my Z-score. I get 1.83. Now this is a right tail test, so I worry about my right tail being bigger than the critical value. I go look on my critical value for a right tail test. 0.05 is 1.645. And I find that my 1.83 is bigger than 1.645. It's a right tail test. So I reject H naught since the Z-score is bigger than the critical value. You learning things? So the conclusion is evidence suggests that the healthcare costs are greater than 1250. Evidence supports HA, that the healthcare costs are greater than 1250. And this is a two-tail critical value approach. And the summary of the problem is here, and you read the problem and get all this data from it. And we will get so now we have to compute compute the Z-score, 69. The X bar was 69, mu is 60, so 69 minus 60 divided by population standard deviation, square root of n, 2.1. And for two-tail, at 0.1 level, my critical values are plus or minus 2.575. This 2.1 is less than 2.5, so I do not reject H naught, since this is a two-tail test. And my conclusion is that there's not enough evidence to support the mean number of text messages differs from 60.
So how do you know to reject it if it's less than 2.575, but it's greater than negative 2.575?
I am so happy that you asked that question, because that means you're paying lots of attention and comprehending. And I'm backing up to this picture. That one. So the critical values are on a two-tailed test will be plus 2.575 here and minus 2.575 here. So if you have a z-score that's greater than 2.575 over here, you would reject. Or if you have a z-score less than minus 2.575, you would reject. But you don't reject in the middle. And that number we had was in the middle, was right here.
Got it.
2.1 something or something like that.
Okay, thank you.
Great. That's a great question. Thank you for asking. Get up there to where we're supposed to be. Two-tailed critical value. That's the end of that. Then I have a set of problems worked out where the p-value solutions are to each problem. And this will be it. So this is the same problem, left tail test, that we had with the eating meals out, although we'll just solve it with the p-value. So H naught was the same, and alpha, n, and sigma are the same, and x bar is the same. I compute my z-score, and I get minus 1.882. But what you do now is you go look in the table, in your table B, and you'll find z-score minus 1.82, and you'll go and find the area to the left, because it's a left tail test, and you'll find that area is 0.0344. So my p-value is 0.0344. Okay, and then you compare that to alpha. And remember, the rule was to reject H naught if the p-value is less than alpha. P-value is not less than alpha, so I do not reject. See how easy that is with the p-value?
Yeah, it's a lot easier.
It's a lot easier. Yeah, I mean, right. It's just bippity bop. So the conclusions does not support that less than 700 meals are eaten out. Okay, and then the same thing with the right tail approach. We have those same numbers, and we compute z-scores 1.83. It's a right tail test, so I go look up 1.883, and the area of the area to the right is 1.083 now. Of 1.83 is 0023. I should have put in another step there. Let's see, did I? No. So if you go look up 1.83, you should find probably 9977. And then the area to the right would be 1 minus 0.9977, which is 0023. So now my p-value is 0.023. That's definitely less than the alpha, so I reject H naught. This is the hiccup with the right tail test, is that you have to make sure you get the right tail area and not just look up in the table what the answer is. And the conclusion is that healthcare costs are greater than $12.50. Because I'm rejecting H naught, I am supporting HA. And then the p-value approach, this is the same problem with 60 texts per year. I don't think I read this one before, but H naught was 60, HA was mu naught is not 60. There's the alpha and standard deviation. There's X bar. I compute the z-score. Z-score is 2.10 still. And this is a two-tail area. So I go look up 2.1 in the table, and I will get a number that is 1 minus this. And so I will really get 0.9821. And so, but I want the right tail area, that's this, but I have to multiply this by 2 to get the total p-value. So that's the p-value, and I do not reject since my p-value is greater than alpha. And I make my conclusion, there's not enough evidence to support the mean value. To support the mean is not 60. If the z-score had turned out to be negative, the answer would have been a negative 2.10. You would have the area to the left is 0.179. The p-value is 2 times that. So either way, you're going to get the p-value is 0.358. Okay? That's all the video I have for that set of slides. I expect you'd like me to post those videos. Is that true?
Yeah, if you can.
Yes, please.
I have the technology to support that. How do you want me to label them? Because they're from a different class. And you already have a bunch of videos there.
You could just put like extra slides.
But do you like them better than that other one?
I haven't really looked at the other ones. I read the chapter, but I haven't looked at the other slides yet. So,
Okay.
I mean, these ones were helpful with the problems,
Okay.
walking them through.
All right. So I will add those slides too. All right. Add chapter 9. Well, these are chapter 9 slides, but I'm not going to change these slides any because it's too much work to change them. In terms of the chapter 9 and all that other stuff on it, everything else is okay with it. But I'll add those slides. I will add the videos. Okay. Or do you want just the slides? I'll add the videos. You are a not talking group. How many are left now?
No,
Pardon?
there's 9 of us.
There's still 9. Great.
Yeah.
Do you want the videos?
Yeah. Post the videos as well so that we have those of you like explaining them.
Yeah, they are all done. The videos are all done.
I didn't know there was videos, so that sounds good.
Yeah, I have these slides. These are for a different class for which I made videos. But
Oh, I see. Okay.
it was a totally different thing. That's a, well, anyway, it doesn't matter. Okay, I will post those tomorrow morning. I've been up since 6:30 doing schoolwork, so I'm going to quit if you don't mind.
No, you're good. Thank
I just
you
still wanted
so
some
much for the
clarification
time.
on the discussion assignment.
Oh, yeah, that's right. You wanted the discussion clarification. Let's go look and see what.
Yeah, it looks like the Excel document might not be set up correctly.
Oh, let's see what's the best way to do that. That's to do this and to go up to discussion 5, is it?
4, discussion 4.
Which module is that in?
7.
Module 7, discussion. There it is, discussion assignment. Let me see what the discussion assignment says. Oh, this was not what you needed to see at all. Oh, that is really, yeah. Let's look at that. those are the responses. Oh, never mind. Let's see. Probably false alarms. There we go. So let me share this screen with you for a second. Okay, so let's make sure we're talking about the right thing. Okay. Let's see, I don't want that anymore. I want that right now. Don't need that. I need to find my stop share. That's what I need to do. Stop sharing. Then I can share this other screen. I wonder if my computer is running out of space. Share screen. So is that what you were looking at?
The one I have looks a little bit different. For the calculations, it just says probability of not having disease, probability of a false positive, and probability of a false negative. I mean, it looks similar to that, but, and then the outputs. Oh wait, that's it. That's the one.
Okay, so that's the one I gave you.
Yes. So when you plug the numbers in, so like the first line example on the Microsoft Word is the prevalence is 0.2.
Okay.
And the sensitivity would be, I think they're the same, 0.85 and then 0.95.
Okay.
But the way it's set up, shouldn't it, for the, on the outputs where it says probability of false negative, the next one down, the probability of false negative, shouldn't that equal, see how on the formula bar it says D3? So it's multiplying the prevalence rate of having the disease. Shouldn't it be the times 0.8, 1 minus 0.2?
See, this is the probability of disease and a negative test.
Because you had posted a website, the, what is it, Math is Fun website, and it has the tree diagram, and that's how I've been solving these because it's much easier to see what you're doing. So for the tree diagram, it would be 0.2 and 0.8 for having it or not having it, and then you split those up each into whether they had a yes or a no on the test.
Right.
So for that line, the false negative, I'm sorry, I have all these notes here. I'm trying to see if I'm looking at the right one. For the false negative on my notes, I actually have 0.03. And on there it says 0.01 because it's multiplying it times a different number.
Well, there's the 0.3 right here. Oops. Darn it. Escape. That cell. I just filled in with yellow.
Uh-huh.
That has the disease with a negative result.
Okay, so are those the numbers that we're supposed to use?
I don't remember what this other box is for. I think these words are wrong. This is, let's see, what is this? 0.3 is equal to D3. D3 is 0.2 times 1 minus D4. Test produces a true positive.
So are those the numbers you want us to use? So for the Word document, the first one asks
Yeah, I think this is, I think.
probability of having the disease, assuming the test was positive. So the true
Yeah,
positive.
I think you want to use this table.
Okay, so the 0.17 and then the false negative, the 0.03.
Yes.
Okay.
And then the question of the, what was that question you have? If you have cancer, you have the disease,
Right.
given that you have a positive test, what's the probability?
So that would be 0.17.
I have a positive. No, that you have cancer, given that you, no, you assume you have a, you assume you have a positive test. So you're in the 21 group, you're in this number over here, this number that I'm just filling in with this yellow. Over here, you're in this row, you have a positive test, and you have the disease, so it's 17 over 21.
Right, that's what I wasn't sure. I had done it that way the first time, and then when I went back and I read that in the directions, it says just fill it out and use the calculation. So I kind of didn't know if you wanted to find the probability of a true positive or the probability of having the disease with the positive test. So I did it that way, and when I divided, I got, where is it? I got 0.8095.
Sounds right.
Okay, so that's the way to do it.
Right.
Okay.
So, you know, the important thing there is that when you come back with a positive test, you've still only got an 85% chance of having the disease, given all these other numbers. I mean, and that's why, I mean, if you put a small number up here, 0.1, 0.02, 03, I mean, you really reduce, even though you have a positive test, you still only come back with a 7% chance of having the disease.
Right, okay.
Yeah.
So if I already had posted on the discussion board, can I just reply to my own and like
Sure.
do that?
Yeah, sure.
Because I didn't know which one to post, and I posted, of course, the other one, and I had done it both ways, so I'll just post it with the
Right.
this way. Okay. Thank you for clearing that up.
You're welcome. Okay, I think we're done for the night. Okay?
Okay, thank you.
Thanks, everybody. Thanks for sticking it out. Bye.
Bye. Good night.
Night.